Okay, so the problem about Lola and her little toy. So it's a little springy cord with a mouse attached to the end, and this is sort of the fixed point up the top, which is attached to a door. The string behaves like or the cord behaves like a spring, like a Hooke's law spring. So it's got a spring constant of this much. Lola grabs it on the ground. This is Lola, represented by the box, obviously. And Lola pulls it horizontally and then lets it go. And we want to find out, well, some things about it, right? So first thing I want to find out is suppose Lola grabs the mouse when it's hanging vertically, like this, and then she pulls it 3 meters horizontally. So what we have here is she goes a 3 meter horizontal distance. Okay, and what's the minimum coefficient of static friction that Lola needs between her paws and the ground to hold it in that position? So, the initial, length of the string when it's at rest is 1.6 meters. Now, you might think that this is 1.6 meters is the relaxed length of the spring or the string, and then the mouse would pull it down. But what I said here was to neglect the weight of the mouse. So, among other things, what that means is don't worry about the mouse pulling the string down and giving a little bit of initial initial displacement. Don't worry about that. So Lola pulls it horizontally 3 meters. So this horizontal distance is 3 meters from its starting point, which was this height or this distance below there. So first thing we want to do is find out how far the string gets extended. Well, the spring is a string, right? So how far does this cord get extended? Like this much. And what I'm going to do is call that length L. So L is going to equal, or this is just the hypotenuse of a right triangle, right? So L squared equals the horizontal leg squared, so 3 meters squared, plus, and then 1.6 meters for the vertical one squared. And as it happens, I admit I picked the numbers to turn out nicely. That gives a length when the string is extended of 3.4 meters. So what happens here is we get the spring starting at 1.6 meters, and the final length of it is 3.4 meters. So that means that its extension is the difference between its final length, this, and its initial length, this. And so the extension is 1.8 meters. Okay, so that's important because then we can find out how much force the spring string cord is exerting. Okay, so the magnitude of the force exerted by the spring is going to be, ouch, sorry, let's see. So as usual, my handwriting is horrible, but the force exerted is going to be K times X, which is going to be our spring constant K, 8.5 newtons per meter. Okay, 8.5 newtons per meter times 1.8 meters, which comes out to be, let's see, 2 times 8.5 would be 17. And so then we subtract 0.2 times 8.5, which is 1.7. So 17 minus 1, am I right? Okay, yeah, 17 minus 1.7 is 16 minus 15.3 newtons. Okay, so that is the force exerted on Lola there by the spring. Sorry about the colors. There we go. Oh, and get out of here. Okay, so the important thing there, okay, is that this force acts like that. So this is the spring force acting on her. What else acts on Lola here? Well, we've got gravity. Okay, I'm sketching in forces here. We've got a normal force from the ground. And what else could possibly be keeping her from sliding back over this way when she pulls it? Well, static friction, right? So it must be the friction between her and the floor that lets her do this. So I'm going to call that F, okay, frictional force. So doing an FBD on Lola, let's go with FBD on Lola. Okay, do an FBD on Lola. We've got those forces. We've got F. Come on, there we go. The normal force, we've got her weight, we've got the friction force, and we've got the spring or string force, okay? And what I'm going to do is I'm going to define, you have to pick some angle to use here. Well, yeah, you pretty much have to. So what I'm going to say is this angle theta here is what we're using, and that's this angle here. And theta, in fact, we can figure out very easily. We don't even have to figure out theta. We can just get its trig functions from this plot or from this diagram here. So let me go sum of forces equals ma, which is not really, well, yeah, anyway. Okay, it's true. It's just, I'm saying it's not required here. Okay, so component diagram. Ah, what the hell? I hate that. So what I'm going to do now, zoom, and then I want to unzoom it and get it back to there. All right, now just stop with that crap. All right, so normal force up, gravity down, and friction force to the left. And then, oh, by the way, the coordinates we're using, x and y, like that, right? So then this one is going to be the string force, or the force from the cord, or whatever you want to call it, times cosine theta. Make our dot bigger so that we can fit in fs sine theta. Okay, so now we need to, Lola's in a state of what we call static equilibrium, which means her accelerations are 0. So we got to actually, compute these things. Sum of force in the x direction, we have negative friction force plus the spring force times the cosine of theta equals her mass times her x acceleration, which is, of course, 0. Okay. Sum of forces in the y direction is going to equal, we've got the normal force going up, we've got spring sine theta, we've got gravity going down, and that's going to equal may, which is also going to be 0. Okay, trust me, that's a 0. Okay, so let's get out here, and what we want to find is minimum value for the coefficient of static friction. So the coefficient of static friction is, let me go with here, we've got mu s, actually let me do it up here. Whoops, whatever. Okay, so mu s equals, remember it's the friction force, in this case static friction, divided by the normal force, okay? And again, if we want the minimum coefficient of friction, that's what we have here. So don't worry about the less than or equal sign in this case. So I want to solve for this and this, okay? So very easily, we can take our x equation and go, the friction force equals, so because this plus this equals 0, I'm going to say the friction force is just equal to the spring force times the cosine of theta. And we can say the normal force is equal to, the normal force is equal to the weight of Lola minus fs sine theta. Okay, so now let's see. This is a handy place to plug in cosine and sine of theta. So recall this angle is theta. You don't need to figure out what it is because remember the hypotenuse is 3.4 meters, the horizontal leg is 3 meters, and the vertical leg is 1.6 meters. So the cosine of theta here is going to be 3 divided by 3.4. And in fact, we also know that the spring force here is going to be 15.3 newtons. So I'm going to go ahead and plug this in, 15.3 newtons, okay? And then the cosine of theta is 3 over 3.4, okay? And that is going to be, let's see, 17 times, so 17.9, let's see, so 4.8, yeah, 4.8 times 3, which is, I want to say it's 14.4 newtons. That sounds right. Okay, 14.4 newtons. The normal force is going to be equal to Lola's weight, which is 3.8 kilograms. Remember, we're neglecting the weight of the mouse. If you wanted to add in the mouse, you'd be at 3.82 kilograms, okay? You can do that if you want. You can not do it if you want. I don't care. 3.8, and I'm just going to use 10 for G because using 10 for G is what awesome people do. Okay, so meters per second square. Well, except on WebAssign. WebAssign doesn't let you be awesome. Sorry. Okay, so there we go. And then minus 15.3. Okay, well, actually that's 15.3 newtons. Okay, times, and then the sine is 1.6 over 3.4. So the sine of theta, 1.6 over 3.4. And then, what did I say here? 4.8, this times 1.6 is, oh boy, let's see. 4.8 to 1.6, I think is going to be 512 plus 768. I think that's right, because it's a little more than half of this. Yeah, okay, that's right. So 7 point, I'm just making it smaller. Well, so this is going to be 38 newtons, okay, minus 7.68 newtons. Is that right? No. Wait a minute. Oh, yeah, it is. Okay, so what we're going to get here is this is going to be 38 minus 7.68, so 30.3 newtons, okay? So now we take this here, this mu s equals friction over normal, and we plug in 14.4 newtons over 30.3 newtons, and I'll tell you right now, I cannot do that one in my head. So whatever that comes out to be is the answer. Stalling. Let me, yeah, well, I don't even know how to pause this thing. Okay, here we go. So 14.4 divided by 30.3 equals, okay, think for a moment about what your favorite fruit is, and we'll discuss that later. Okay, is 0.475, so about 0.475. Okay, so that's part A. That's the static friction coefficient Lola needs in order to hold herself at this position. And basically, she tries to pull herself as far as she can. I wish I'd been able to write this problem and in a way where I give you the static friction coefficient, and then how far does she pull it? You know, so given that she has a static friction coefficient, say 0.5 or 0.4, how far can Lola pull it? Because that's really the problem Lola's interested in, right? She wants the most exciting snap possible when she lets go. And so she would want to know, if I have this coefficient of static friction with the ground, how far can I pull it? Unfortunately, that turns out to be a really obnoxious problem to solve. And in fact, it's not something you can solve very easily in closed form. You'd really have to plot on your calculator and everything. So I don't want to give you that for a test review. So let me just label this up here so I can save a little more space. That is value